Welcome to Medical Radiography Exam, India's first radiology website. For more about us, search on Google Made Radio Exam. Please like and share our video. Subscribe our channel. Hello friends, today's topic is Radiographic Grid, its construction, types, use and grid ratio, grid frequency and contrast improvement factor K. Radiography Grid. An X-ray grid is a filtering device that filters out randomly deflected radiation, scatter radiation, that can obscure or blur an image produced by the X-ray machine. In this figure, most of the scattered photons, traveling at an angle to the primary beam, will not be able to pass through the grid but will be intercepted and absorbed as shown in figure. Some of the rays traveling at right angle or nearly right angle to the grid are also stopped due to the finite thickness of the grid strips, again shown in figure. Both the primary beam and the scatter are stopped in this way, but the majority of the primary beam passes through the grid along with some scattered radiation. History. Gustav Bucke, 1880 to 1963, a German-American radiologist, invented anti-scatter grids and he filed for a patent on a stationary grid in 1913. Moving grid was later added by American radiologist Hollis E. Potter to improve it. The shift from tiny glass photographic plates to film in various sizes was made easier by the Bucke-Potter grid. Construction. The grid is constructed of a series of alternating parallel strips of lead and a radiolucent substance such as a plastic, carbon fiber, aluminium, even paper. The majority of grids are linearly shaped in one direction, usually along the long axis of the detector. As demonstrated in above figure, the majority of scattered photons that are traveling at an angle to the main beam will be unable to pass through the grid and instead be intercepted and absorbed. Due to the finite thickness of the grid strips, as is again seen in above figure, certain rays that are traveling at right angle to the grid or approximately at right angle to the grid are likewise blocked. This stops both the primary beam and the scatter, although most of the primary beam and some dispersed radiation still pass through the grid. Types of grid. X-ray grids are divided into following two types based on their movability. First, stationary grid. Second, moving grid. X-ray grids are divided into following four types based on their designs. There are: first, parallel grid. Second, focused grid. Third, Criss-Cross Grid. Fourth, Tapered Grid. Stationary Radiography Grid. Gustav Bucke developed the stationary radiography grid in 1913. It was made up of thick lead strips that were organized into parallel series that crossed each other at an angle. The current stationary grid comprises of thin, tightly spaced lead strips that are separated by a radiolucent substance, often metal or plastic. The grid may be either a parallel grid, in which the lead strips are parallel to each other, or a focused grid, in which the lead strips are canted or angled toward the center. The lead strips of the fixed grid leave blank or white lines on the film, which is one drawback. Grid lines are the name given to these lines. Modern grids need a smaller increase in patient dosage than older grids and lessen the sight of grid lines. Nevertheless, because this grid is so costly, mammography is the only application where it is often used. Moving radiography grid. Using a stationary grid imposes a radiograph of the grid as a sequence of lines on the image due to the absorption of the primary beam. Modern fine grids reduce but do not eliminate this impact. The effect can be overcome by moving the grid during exposure so that the image of the grid is blurred out. The radiologist may become distracted by this grid design. Dr. Hollis Potter originally proposed moving the grid sideways across the film during the exposure as a remedy to this issue in 1920. Because the grid strip shadows are softened, they cannot be seen. To produce this movement, a variety of devices have been used over time, including electric motors and cocked springs. Parallel grids. Parallel grids have lead strips that are focused to infinity and are parallel to each other in their longitudinal axis. The primary X-rays have a parallel trajectory. In this figure, lead strips are shown in black and primary rays shown in green color and scattered rays shown in red color. In this, the lead strips are parallel to each other. Focused grids. To match the beam divergence from the focal spot to the detector at a certain source to detector distance, focused linear grid is used where the lead strips are progressively angled on moving away from the central axis. In this figure, lead strips are shown in black and primary rays shown in green color and scattered rays shown in red color. In this, the lead strips are canted or angled toward the center. Criss-Cross Grid. Crossed stripes, which are also available with rhombic angle, make up a crossed or crosshatch grid. Lead strips in both directions, perpendicular to each other. The usage of a tube angle is not appropriate for these kind of grids. Such grids must be set up precisely at a right angle to the beam in order to be effective in removing dispersed radiation. As a result, their usage is constrained. In this figure, lead strips are shown in black. It was made up of thick lead strips that were organized into parallel series that crossed each other at an angle. Tapered grid. A grid that functions like a focused grid but with the surface tapering into the center. The tapering surface is directed towards the focus point and all of the strips are parallel to one another. This figure shows simple grid. In this figure, lead strips are shown in black and primary rays shown in green color and scattered rays shown in red color. In this, the lead strips are parallel to each other. In this figure, small t denotes the thickness of lead strips. In this figure, small h denotes the height of lead strips, and in this figure, capital D denotes the distance between lead strips. And here grid ratio equal to small h by capital D. And here grid frequency equal to 1 by small t plus capital D. Contrast improvement factor K. As grids can remove up to 90% of the scatter, there is a large increase in the contrast in radiographs when a grid is used. This increase is expressed in the contrast improvement factor K, where K equal to X-ray contrast with grid by X-ray contrast without grid. K typically ranges from 2 to 3, although it can go as high as 4. Typically, increasing the number of grid strips per centimeter results in larger values of K. The main beam is blocked by the grid when these are enlarged, therefore more of it is lost. Grid ratio. The height of the lead strips divided by their distance between lead strip is referred to as the grid ratio. The dimension of the lead strip that is at right angle to the principal radiation reaching the grid is referred to as the thickness of the lead strip. The grid ratio will alter if the distance between the strips is decreased without reducing the height h of the strip. When that happens, the grid is too thin to be of any use. Grid ratios range from 8:1 to 16:1. Only exposures at a kilovoltage of less than around 85 kVp are expected to require an 8:1 ratio. There are two grid options available for exposures at higher kVps, 10:1 and 12:1. The majority of departments undoubtedly choose for the 12:1 grid because Despite the increased dosage to the patient, it is believed to improve contrast for thick sections. Because the grid structure only permits a certain angle, a greater grid ratio will often reject scatter better than a lower grid ratio. Nonetheless, a higher ratio grid's use is often associated with a greater dosage penalty. For screen film imaging, this is known as the Bucky factor. The anti-scatter grid's radiation to transmitted radiation ratio is known as the Bucky factor. Because each increase in MAS correspondingly increases dosage, the Bucky factor indicates the higher radiation dose needed by the usage of anti-scatter grids. Grid frequency. The quantity of lead strips per inch or centimeter is known as the grid frequency. Stripes get narrower as the grid frequency rises. The range of grid frequency between 40 and 50 lines per centimeter for low frequency grids, 50 to 60 lines per centimeter for medium frequency grids, and 60 to above to 70 lines per centimeter for high frequency grids. With systems that have a moving grid assembly, sometimes referred to as a Bucky device, that oscillates throughout the exposure to blur the grid lines, low-frequency grids are employed. Typically, fixed grid holders are utilized with medium and high-frequency grids, for example, portable radiography and many digital radiography systems. The usage of high-frequency grids is crucial for digital radiography systems to prevent aliasing artifacts, which are caused by inadequate sampling of high-frequency patterns and appear as low-frequency, aliased signals in the output signal. Thank you for watching. Medical Radiography Exam family wishes you and your family happiness and prosperity and healthy life.